Afternoon, everyone. I hope you are enjoying the conference, and I hope you will bear with me for next 50 minutes. I know the conference has been long, and we are all full of experiences, so bear with me for the last one. As already mentioned, I am a software engineer at Microsoft. More specifically, I am a maintainer of system and security namespace in .NET Runtime. That's where our abstractions for TLS are that our users can use. I also do some small contributions to the system cryptography namespace, where are all the other cryptographic primitives. Those areas are somewhat related, and both of these are backed by OpenSSL, at least on Linux. What we will talk about .NET. Obviously, we will also talk about Linux. It sometimes surprises me that there are still people who think that .NET is something that is Windows only. So I will do some quick introduction and how come that we can, for more than 10 years, we can use .NET on Linux. We will be talking about OpenSSL and Schannel, just a little bit of comparison, because those are the two TLS stack implementations which we are primarily using. Schannel on Windows, OpenSSL on .NET. OpenSSL on Linux. I will also talk about how we target .NET, how we compile .NET so that it works on multiple Linux distributions with all the various OpenSSL versions which you can find in the wild. And I will also introduce you to some current challenges that we are facing with this integration, and which we are we will be attempting to solve in the next couple of releases. So let's start with .NET and Linux. As I mentioned, many people think that .NET is only Windows only thing. There is this thing called .NET Framework, which is the original implementation that has been there for decades, and as mentioned, is Windows only. However, at some point, it has been decided that it would be nice to have something cross-platform and re-implement it and basically repair some of the maybe design mistakes that have accumulated over the years. So at some point, the .NET Core development has started, and in the year 2016, we had first cross-platform .NET release, and ever since then, every year there is a new release. This year will be the 10th one, and since then we work on multiple OSs, including macOS, even Android, and some of the more exotic ones like web browser, Wazi. And in order to do that, .NET relies on libraries that are present or ubiquitous on the particular platform. So we don't want to implement our own cryptography primitives because that has some challenges, namely getting them right, obviously, but there are some certifications, there may be some export restrictions in some countries. So in order to avoid that, we use already existing implementations and leverage those. So as mentioned, on Windows we have Schannel, on Linux we have OpenSSL, OS X has something called Security Framework, Apple has their own interfaces, and etc. Another thing that this allows us to do, and probably the bottom point is the most important, because we don't carry our own implementation, we can respect the global configuration on the system. On Linux, it's present in the form of some OpenSSL config. On Windows, again, it's some registry configuration. So we basically behave nicely with all the other applications which use the same thing on that particular system. So that administrators can basically have one place where they need to make any changes that they need, and .NET applications will play nicely with that. It also has some downsides. One thing is that we are using different implementations everywhere, so we need to make sure that they behave somewhat consistently or similarly, because we provide uniform API across all the platforms. So sometimes there are some bridges that we need to, or gaps that we need to bridge. And it's even more apparent on Linux, where there are multiple OpenSSL versions that are supported at any given moment. Some distros are shipping, from today's perspective, are shipping 3.5, some are shipping 3.0, some even are still using 1.1.1. So we need to make sure that .NET can work with all of these. Small comparison between OpenSSL and Schannel. Why is it important? Because I mentioned that .NET started on Windows only, and there it was backed by the Schannel implementation, and that had some influence on the API. And when we started to work on making .NET cross-platform, we didn't want to change the API. We wanted to preserve some backwards compatibility with .NET Framework to make it easy for our users, our customers to migrate to the new .NET. And what we basically had to do is that we had to make some cut in the middle of the library and replace that with some bindings to the OpenSSL security framework or whatever it's present on the target system. So basically, just a small comment why the API shape is the way it is. And specifically with regards to OpenSSL versus Schannel, there are some architectural differences that we need to work with. And the chief one is that, for example, when you load a certificate with a private key on Windows, when you are using Schannel or crypto APIs over there, the bytes of the private key are never present in the application's memory. So if for some reason somebody managed to memory dump the application process, they would never be able to find the private keys. And the way it works is that there is some privileged process, local security authority service, which handles all the sensitive information or operations with the private keys. And there is IPC channel between the application and this privileged process, which does everything. So the TLS handshake actually includes lots of IPC back and forth between multiple processes. This one specifically is mostly a matter of documentation, but there are also some things which don't work so well with the Schannel model. We have some long-standing issues that it's somewhat hard to specify which certificate chain should be used over the wire on Windows, because since the handshake happens elsewhere, the only way to make Schannel aware of all the intermediate certificates is to put them into the system store somewhere, and that's something that we have been trying to work around for quite some time. On Linux, because OpenSSL has everything in the application process, that's fairly simple, and it actually works, I would, in my opinion, much better, at least from user experience perspective. I already touched on machine stores. Windows has some concept that are different certificate stores for certificates that are supposed to be used for different contexts, different things. And since we already exposed some API for that to manage those stores and access them, we basically had to emulate those on Linux. So the cryptography maintainers decided to do some some directory in the home folder, and that also seems to work reasonably. And probably the most important, or the one that I think was visible most and implementing bindings for OpenSSL, that when verifying certificates with Schannel or crypto API, the process which does it, the process which does it is willing to download all the necessary information if it was not explicitly given. So with certificates, there is a thing called authority information access, which tells you where you can find the issuer certificate. And sometimes it happens that for some reason during the handshake, you receive only the leave certificate. And in those cases, Windows would be able to figure out where to find the missing certificate and then download it and use it for validation. At that time, that was still like in the old OpenSSL 1 days. There was no such functionality in OpenSSL, so we had to implement it manually in C#. If I remember correctly, nowadays there is in OpenSSL 3 there are some functions which can do that for you, but we are still using the ones that we have implemented ourselves in this context. So the meat of the presentation, and the biggest part, how do we actually build .NET so that it's able to use So it's able to work on all these different Linux distributions. And basically what the goal that was set before us is that ideally we want to have single set of binaries that we would publish either on the website or in the package feed somewhere. And when users download those, it would work on any supported Linux distribution. And yeah, so that also is probably not the Linux way. The Linux way might be to build separately for each distro separately, but this also allows our users to do the same thing with their own applications. So when users download the SDK, they can build their own .NET application, and they can be sure that that application will run in any supported distribution as long as they match the CPU architecture. And in case of Linux, they also need to match the glibc versus muscle variant of the operating system. So the challenge is, how do we design it, how do we implement it in such a way that all this works? So as I mentioned, the glibc is the big one. Different distros are using different glibc versions. Obviously, the newer distribution, the newer glibc version. So in order to support the broadest spectrum of glibc versions, we need to pick some minimum version and then use some distribution which uses that to build the actual release package of .NET SDK and runtime. Yes, there's a question? Yes, C++ CLI and transition to manage objects. So C++ CLI is something which wasn't ported over to .NET Core. That was left at Windows because there were some difficulties when porting it, and there was not enough demand for that. So, yeah, maybe if that answers the question, that part is still left Windows only, I believe.
And how do you do?
We are using the foreign function interfaces. We are calling into the C code and basically are wrapping pointers to all these structures. So we are not actually generating managed types, so C# types based on whatever is in those libraries. We do interop as we would normally do with using pointers. Okay, glibc compatibility. Basically, what we do is for the previous releases until now, we have used Ubuntu 16, which is more than 10 years old, or almost 10 years old. In next version, we decided to upgrade to Ubuntu 18, so we are slowly moving forward. But still, like, this means that basically on any currently supported Linux distribution, when you download those binaries, they will work. The fact that we are compiling on very old distributions will also come back later when we talk about OpenSSL. So please keep that in mind. So what about OpenSSL? When applications want to use third-party libraries, they have basically two major choices. They can either link statically, which has many implications. So when there is a vulnerability in OpenSSL, it would mean that first we would have to react to it and update all the SDKs with the newer patched OpenSSL versions. But then at the same time, same thing would have to be done by our users. So they would have to recompile and redeploy all their applications. So that's not something that's very practical with something as sensitive as cryptography. So we wanted to avoid this. And the other one is dynamically, but when we are compiling on Ubuntu 16, which has, I believe, OpenSSL 1.0, then that will not really load on on Ubuntu 22 or 24, which is using something more recent. So we have to do something a little bit different, and it's closely resembles the dynamic linking, but we are basically doing it manually, that we load the library using DL load, and then we probe it and examine it, what functions it provides, and we can fill in the rest if we need it. And that's what I'm going to talk about in during the presentation, how we are doing this part. Next. Okay, so just a small diagram which shows how this fits together. We have some applications just running in .NET that's purely user code, and we have some portions of the .NET runtime which is also written in C#. This portion is cross-platform and is basically unchanged between all the operating systems to which we ship. But at some point, we need to specialize the code to use the things that are present only on the operating system. So that's something that we call PAL layer, platform access layer. And specifically on Linux and macOS, we also include some small native binary, because some things are easily done or more efficiently done when done purely in native than marshalling back and forth and crossing the language boundaries. So it's a little bit more practical to have some small binary inserted between the system libraries. So next, I will be talking mostly about this library, how we are actually loading OpenSSL, and how we are examining its functions. So initialization. First, we need to somewhere load it. We are using DLOpen, as I have mentioned a little bit before. This is just a small wrapper around that. And then we have some function which decides which version are we going to load. There is some branch which allows you to override which OpenSSL version is going to be used. That's sometimes useful when debugging, when we build let's say when you now build the main branch of OpenSSL, it has version 4. So that's one example where you can actually use this when you are doing some local development. But also in the past, it was useful when there was OpenSSL 1.1 and OpenSSL 3 coexisting on the same system during some transition period. So user had some control over that. And basically, we try from the highest version that we consider supported. So first 3, if not, then 1.1, and then down the list, which I didn't include in the slide. And once we load that, because .NET is JITed language and we want to be kind of lazy, we don't want to do all this work and many other things as well if the user application does not end up using cryptography at all. So we also need to make sure that this happens only once and at the appropriate moment. So we just wrap it in a pthread once, and that does the trick. So now we have loaded the DLL into memory. We have a pointer or handle which we can use, but so far we don't have any functions available to us. No function pointers are loaded yet. And there is where the most of the machinery is. So what we have in our source code, we have some big macro for all OpenSSL functions, where every function which we are ever going to use from OpenSSL is listed. And there are some tags around it. So there is required function, there is fallback function. I will be talking about these in a moment, because that's what actually allows us to handle different versions, because some functions may be missing in some versions, and etc. And then we do some macro magic to define some external pointers. So for example, with the ASN D2I bio, this piece of code will define ASN1 D2I bio underscore PTR. And that's what where we would eventually load the function pointer, and through that function pointer we would be invoking those functions. And to make it convenient and hide all this complexity from average developer who was going to contribute to .NET, we define separate macro for each of this function to basically remove the underscore PTR prefix, or suffix, I'm sorry. So once all this is done, the internal code which is using OpenSSL looks just ordinarily code which is using OpenSSL, and all this complexity is basically hidden from the average developer. So back to the initialize OpenSSL shim function, which I showed earlier, where we had the loading of the library, loading specific version. This is the place where we actually handle different functions differently. And there are several categories. The most obvious one is required function, which is a function which we need in order to work properly. And if you don't find it in the SO, we just abort the process and say, hey, like, we weren't able to find, I don't know, SSL new or something vital, and leave user to work around that. There are also, because the code still supports some now very outdated versions, so during transitions between 1.1.1 and 1.0, there are some substantial changes. So we have separate macro which will load the function only when we are running on something newer than 1.0. We also have light up function, which is just a weird way to say optional function. So that's something which we use for newer features that are available on only newer versions of OpenSSL. We have fallback function, where we are able to provide our own implementation when there is no such function in the shared library. And we also have some macro which is able to handle renames. So I believe there is some convention in OpenSSL. There used to be like get something, and then it became get 0 or get 1, depending on whether the reference counter was increased or not. So this macro is able to handle transition between get and get 0 or whatever we are going to use. Yeah, and then we have legacy. That's something that's only for the very, very old OpenSSL versions. I have some specific examples. So fallback functions, those are the ones where we can fill in the blanks ourselves. And those are basically used to transition the gap where in some version of OpenSSL there was a macro, and in later versions it became a first-class function. So obviously when we load the old version of the library, there will be no such function in the library. So in that case, we can just supply our implementation, which is just the contents of the macro. So SSL context set options is one of those. There are tons of these. Missing functions are similar, slightly different, sorry. Those are functions where we basically check for some functionality, and that functionality is usually expressed by specific functions which we are going to call in OpenSSL. This example is probably the more intuitive one. So in OpenSSL 3, there is the new concept of providers, and some algorithms which are considered legacy are disabled by default unless user explicitly opts in via provider try load. And what we are doing in .NET to bridge this difference is that when user is trying to use something which relies on these old algorithms, I don't remember exactly from the top of my head, maybe RC4 or MD5 or something like very old and unsecure, but some algorithms, some protocols still use it for various reasons. So we basically transparently load it for them whenever needed. And if we figure out that this function was not loaded from the shared object, it probably means that we are running some older version of the library where we don't have to do anything to get access to those older algorithms. So this is one of the examples where this plays to hand. Yeah, good that I have included it in the presentation. So very good question which you might want to ask. If we are compiling against OpenSSL 1.0 headers on Ubuntu 16, how do we compile the code which references, for example, this one, EVP key sign message init or something, which is something that is present only in OpenSSL 3.0 or 3.5 and later? I don't remember from the top of my head. And what we basically do is we provide a header file with all the signatures from newer OpenSSL versions which we are going to use. So we basically polyfill these signatures so that code actually compiles, and we have it type checked and everything. So we need to handle like all these cases that we are compiling on old system and loading the newer one. So we need to know the new function signatures. And for local development, also the other direction, that we compile something on something which is compiled against OpenSSL 3 headers, but during the runtime for some reason loads OpenSSL 1. And all these machinery, these macros, these compat header files which contains these signatures, these seem to achieve the trick. Okay, next. Good, so what could go wrong? Well, many things could go wrong, but mostly they have been caught during testing, because when you mess some integration, usually the first time you call the function, it will do some invalid access or corrupt data, and it will fail very quickly. However, there have been cases where it has been much more subtle. And the one that I'm going to talk about is when we started supporting Ubuntu 22, and we got a bug report that on ARM32, the SDK, whenever you are trying to build your .NET application, it will basically fail with some obscure error about no protocols being available, which is something that OpenSSL does when client and server don't have a shared supported protocol. And why that happens is because, like, during the build process, you can download some third-party packages and libraries. So that's why we are doing outbound SSL connections during building process. So bottom line was that .NET was not working well on ARM32 on this very new, at the time, very new distribution. So we decided to investigate, and without working too much around it, it was caused by some breaking change between OpenSSL 1 and 3, and because Ubuntu 22 was the first distribution, or first Ubuntu distribution to ship OpenSSL 3, that's where we hit it. But then the question is, like, why didn't we hit it on all the other platforms? And the reason is, I will unroll these. So when we compile OpenSSL against the older headers, we are using the old signature of the set options, which is accepting 32-bit parameter for the options flags. But then at the runtime, we load a library which is accepting 64-bit flags in that same function. But we are still invoking it via the pointer, which is accepting 32 bits, the function pointer. So basically, it boils down to different calling conventions on ARM32, where, because it's 32-bit platform, you need to handle 32-bit and 64-bit parameters differently. And bottom line is we were supplying garbage to OpenSSL. So this is a screenshot from the debugging session when I had the Eureka moment. So there we have the function which we are calling the set options. We were passing some flags, which should translate to exactly 2 bits set in some integer. And when we step into, we see that there is something which definitely is not just 2 bits set. And when we look into registers, we see that, okay, we actually put it there, but for some reason, the library is reading something else. So how do we fix it? Well, we need to check at runtime what we have actually loaded, and we need to do some pointer casting and some shuffling to make sure that we put the parameters where they belong. Another challenge which we have faced during the development is when we had to actually load multiple versions of OpenSSL in the same process, which is something that we generally tend to say, hey, like, don't do it, you can break stuff, and it's definitely not something that should be supported. But there's a kind of story behind that actually shows that we actually didn't have at the time a good short-term solution other than doing this. So this was also in 2022, and it was when we were implementing support for the new Quick protocol. We were using the MS Quick library, which is library developed by some other team in Microsoft, and on Linux, they decided to use some fork of OpenSSL because at the time there was no public API which would provide all the necessary functionality to implement Quick on top of OpenSSL. So that's the way they decided to go in order to progress and have something that would compile on Linux. And what they were doing, the MSQuick team, is that statically link the forked version, because you can't really ask users to install your forked and modified versions of OpenSSL. But because the changes were only in the libSSL binary, they still dynamically linked against libcrypto, which is a weird combination, but it seemed to work until we got to Ubuntu 22, because OpenSSL 3.0. Because at the time, MSQuick produced only binaries which used fork of OpenSSL 1.1. So MSQuick tried to load OpenSSL 1.1, found only 3.0, so it did not load. So we didn't support Quick on those platforms. And there were, because Quick was very new at the time, and it was very popular demand to play with it and experiment with it. So users were filing bug report, hey, like I want to use this on this new Ubuntu. What can I do? And one of the solutions was installing some compatibility package which gave you OpenSSL 1.1 libraries alongside OpenSSL 3.0. And when that happened, I don't have it there, but at that point, the application process would be loading OpenSSL 3.0, libSSL and libcrypto to use for TLS and all the other operations. And through MSQuick, it would also load libcrypto 1.1, but because there was no passing of raw pointers to OpenSSL structures between those two libraries, it worked, and it did not cause any data corruption or access violations. Long-term solutions, obviously, better solution would be to produce different flavors of MSQuick based on which base OpenSSL version it was created on. So that's what followed a couple of months later. And future solution, which I believe is already partially implemented, OpenSSL 3.5 exposes the necessary APIs for implementing Quick separately and gives you access to just the handshake part of TLS to do that. So that's something that's going to work in the future. I believe I saw the PR. It's not there yet. I think it works only when everything is linked statically, but it's definitely moving in the right direction. So some of the current challenges which we weren't able to solve at the time, we have long-standing issue about apps which are somehow interacting with servers, with certificates which are somehow connected to large certificate revocations lists. And due to some policies, certificate revocation checking is mandatory for these customers, so they can't really turn it off. And what they notice is that when they have some even simple applications which is just periodically connecting to such a server, the memory usage is gigabytes more than normal person would expect. So our first instinct was, okay, there might be some memory leak. Nothing. We didn't find anything using the usual profiling tools. So we had to dig a bit deeper. So this is parts of the logs where we decided to dump malloc data. The first line is actually from applications log, which says, okay, the application is consuming 5 gigabytes of memory, and only 1 megabyte of that is actually consumed by memory allocated by C# code. So manage is a slang for memory allocated by C# itself. So the rest of the memory is being consumed by something else. And it turns out that malloc is actually holding onto the memory in something called free lists. And although the memory is freed correctly and we are not using it for anything, it is just not returned to the operating system. So it looks like the application is using this amount of memory for no good reason. And you can actually reproduce it separately outside of OpenSSL. It's a known problem of memory fragmentation. I think I have a simple repro here. You make a small application which allocates lots of small buffers in a loop, and later you free everything except the last one. And when you do that, there is also some code which dumps some statistics. When we do that, we allocated something like 1 gigabyte in total with 1 kilobyte buffers, and we allocated this many of them. Once we allocate everything, okay, like total allocated space according to the malloc stats is something more than 1 gigabyte as expected. And when we free everything except the last allocated one, everything moves into the total free space, and the resident memory of the process is staying the same. So it's only after you free the last buffer that you get all the memory back. So in this simple scenario, it might be easy to just like do some rearrangement of how buffers are used, but the problem is that if you have an application which is running many TLS connections, possibly in parallel, and combined with some other things, it's not so easy to just like say, okay, so just like free also the last chunk or something like that to allow malloc to consolidate all the memory. So the few things that have to combine to trigger this thing are that lots of small objects are being allocated, which is what happens when you parse large certificate revocation lists. So I think it's something like if you parse 10 megabytes certificate revocation list, it will allocate something like, I don't know, order of magnitude more, 400 megabytes. However, if you do it repeatedly, the memory keeps accumulating in those free lists. And one thing that does not really help is .NET asynchronous programming model. In short, basically, you have some task, let's say TLS handshake, and whenever you are waiting for some data on a socket, for example, the task, the logical piece of code gets set aside until we have something come in for us from the other side, and then it gets scheduled somewhere on a thread pool and will be picked up potentially by a different thread. So parts of the logically same procedure or function will get executed on different threads, which means they most likely, those pieces of memory allocated from there will end up in different parts of the malloc arenas. And now when you combine it with the small allocations, then you have this problem suddenly. Anything else? Yeah, and obviously, if you keep having new connections and like don't get to a place where the applications just sit still and does nothing, you always have something allocated somewhere, which is probably what's keeping the memory alive and from being released. So we don't have a good solution to that. We have only some workarounds and not necessarily like even good workarounds. First one is just don't parse those lists and don't check revocation. But that's not something that we can decide as library developers. That's something for our users to decide whether they need it or not in their environment. We can do some tuning of the malloc using some environment variables or malloc tunables, but this is also some trade-off between performance and memory. So if we force that only one malloc arena is being used, so everything ends up in one place and does not leak memory as much, then suddenly we have log contention and decreased throughput of the application. So that's also a no-go for many customers. We can say, okay, let's try different malloc implementation. Then again, it's not something that we as library developers can do. We can't just arbitrarily decide to ship another library which replaces malloc. And if we ask our users to do that as a workaround on their side, it complicates development, it complicates deployment because they need to get the malloc, they need to know how to install it, etc. And it does not necessarily need to help. That's also the other thing. There's also something called malloc trim, which is some signal to malloc, hey, consolidate memory as much as possible. But it does not work in all cases. It can help, but in the simple example I showed before, even like the one where you manually allocated many buffers and free all except the last one, in that case, malloc trim does not help either. So that's something that can help, but is not a good solution because also this call can hang for a couple of seconds, so it's not something that you necessarily want to do in your application. And probably the only viable thing for us left to do, which we didn't get around to implement yet, was introducing some internal cache for those certificate revocation lists, so that every time we connect to the same server, we don't have to parse the certificate list every time and then discard it every time and produce this allocation churn. But that introduces complexity. Like every time you introduce cache to a system, there are many problems that you need to think about and lots of testing to be done. So that's also something we have been avoiding for as much as possible, but eventually we will probably need to do that. And I believe that's all I had in my presentation. So thank you very much.
So I have a friend who is really a .NET enthusiast, and he loves like .NET Core, and his hobby projects are like showcase of the best things. But in professional setting, he's often forced to work with .NET Framework. And he's very complaining about it. Like, does Microsoft still care about .NET Framework? Because there is a lot of applications built on that.
Yeah, so the situation is complicated. We obviously care about .NET Framework, but since it's sort of part of the operating system and is automatically updated, we need to be very conservative with any changes that we do to .NET Framework, because we run risk of suddenly breaking millions of users. And like many of these applications are not actively maintained anymore. So when we break those users, what do? Like they can revert the security patches which install the new .NET Framework, but that's obviously not the way. So we have to be hyper conservative in whatever changes we do to .NET Framework, and it boils down to a question: is it a security bug or not? And if it is a security bug, then we do as little change as possible to fix it. But whenever it's anything other, like performance thing or a new feature, we just don't risk breaking something which is basically used by everyone. And it's like the updates are like automatically. It's not opt-in as in .NET Core, where it's your decision to upgrade to the new .NET. With .NET Framework, it just does automatically for you. So it's just
Microsoft still does care about .NET Framework.
Yes.
Sadly, yes.
Like, it's probably something which is never going away because of how many applications are still using it, and which means we have to support it basically indefinitely.
Yeah, thank you very, very much.
Do you have any analytics on, let's say, the distributions that your users are using? And related to that, how do you decide what specific combinations of, let's say, distribution and architecture you support?
Okay, definitely somebody in the larger team has the statistics on the usage. And unfortunately, it's something I don't have answer for. Maybe if you reach out to me later, I can connect you to the right people or find it somewhere on GitHub. .NET Core is very transparent. Unless it's a security thing, we are doing it publicly on GitHub, including all the decision, when do we drop support for such and such operating system or platform. So the information might be available if you know where to find it. So reach out to me and I will try to find it for you.